We're going to use these Bohr model electron energy diagrams to make some calculations involving the relationship between the electron energies and the photons that could be absorbed or emitted by a given atom. So we have two electron energy diagrams, one for hydrogen and the other seemingly randomly for mercury. These electron energy levels that are possible are not just theoretical, they're tied strictly to the absorption and emission spectrum of hydrogen. That is, the observed photon energies emitted are exactly equal to the electron energy differences that are possible in a hydrogen atom. If an electron could have any just random level of energy in hydrogen, then that would infer, or we can infer from that, that hydrogen could emit any possible energy or color photon, and that's never been observed, and it's never going to be observed. We know that because there's a second reason. An electron also has in addition to its obvious particle nature, it has a wave nature, and we'll talk about that later, but waves have particular energies based on wavelengths, and if the electron wavelengths interfered with each other such that the electron disappeared in the atom, well, the atom would no longer be. So the particular electron energies are tied to their wave nature. So another thing to note for the electron energies in hydrogen, which is merely just one proton and one electron, is that the electron energy, what we'll call an electron energy level, the level is proportional to 1 over the energy level squared. So actually there's a negative in front of that. So the greater n is, the smaller this fraction is, and the less negative the number is. That takes a little bit to get used to, but the logic is when n reaches infinity, we want to say that there is zero electrostatic attraction, zero potential energy between the electron and the nucleus. The electron's gone, so there's no attraction, no positional energy, no potential energy. As the electron gets closer and closer, it gets more attracted to the nucleus and therefore lower in positional or potential energy. So all of these other numbers are negative relative to zero, and that goes along with this formula. A more general formula for the Bohr model, which does break down for any system, any element that has more than one electron. So this formula works just for one electron cases, such as the helium plus cation or the lithium 2 plus cation, or certainly for the hydrogen atom, is negative the nuclear charge squared. So with hydrogen, Z is just 1, so it's the same formula as negative 1 over n squared. And we could test that out with some of these numbers. For example, when n equals 2, you see the energy level in electron volts, we don't have this in joules, is negative 3.40. So if we doubled n, so n went from 2 to 4, that would be 1 over 4 squared is 1/16, and 1 over 2 squared is 1/4. There should be 1/4 as much energy of that electron in magnitude, or at least the number should be 1/4 as large. And if you compare 0.85 with 0.30, there is a 1/4 difference. Okay, so that's the mathematical formula for the energy of an electron in a given level n. Alright, so let's look at some of these questions here. How much energy must be added? That means absorbed by the electrons, or an electron. To ionize, that's to bring the electron to the infinite level, basically knocking it out of the atom. If the electron is initially in the ground state n equals 1 versus n equals 2, you can see there's the largest gap between the first and second principal energy level of the electron, and that's quantified in this formula. So let's see how to do that calculation. In just about every calculation in this unit, you want to show that you're following the conservation of energy. Energy cannot be created, nor can it be destroyed. So we write the somewhat trivial statement: the energy absorbed by the electron. And what energy is that? That's the photon that it's absorbing, is equal to the change in energy of the electron. So it's not that difficult when you write something as direct as that. The energy absorbed by the electron is the energy of the photon. Well, what happens to the photon is it goes away. It does get destroyed, it disappears, its energy is absorbed, that packet of energy, but it's really being transferred to the energy of the electron. So every change in science is final minus initial. So final electron energy minus initial. And we don't have to use any fancy formula for that. We do have a whole bunch of energy level values already written. Come to think of it, we need an energy term in the Bohr equation here. This is times a constant called a Rydberg constant, and that is 13.60 electron volts, or in joules 2.178 times 10 to the minus 18 joules. Okay, there was no energy term, so we wouldn't get an energy value without that. Anyway, so specifically here, the electron's being knocked out, so that's the infinity level, and the initial level in the first question is n equals 1. So at the infinity level, there's 0 electrostatic potential energy. I'll put the units at the end in electron volts, and from that we subtract level 1, negative 13.6, much lower in electrostatic potential energy, much closer to the nucleus. So the photon that was absorbed had 13.60 electron volts of energy. How is that an energy unit, an electron volt? Well, the thinking is electrons have coulombs of charge. A volt is a joule per coulomb, so coulomb times joules per coulomb is joules. There is a conversion factor from electron volt to joule. It's just the magnitude of the charge on an electron. But we write that in joules, 1.60 times 10 to the minus 19 joules per electron volts. So electron volt units are more tangible, countable. We don't have any crazy exponents, but you can see as far as in joules, it's quite a small amount of energy per photon. That's why we usually scale them up to moles of photons. And there's our answer in joules, which no coincidence matches that Rydberg constant value to 3 significant figures. Alright, so let's look at B, or I'll just write out the answer to B, and then we'll do part C. So you could see for part B that right from the diagram, less energy is going to be required to knock an electron out of the atom compared to an electron and some other hydrogen atom that absorbs that photon to get knocked out. So just using the energy level already seen on the chart, we get 3.40 electron volts, which for comparative purposes 0.544 times 10 to the minus 18 joules, a lower energy photon than the one that's 2.18 times 10 to the minus 18 joules. A different color light is absorbed. Let's figure out what type of light that is, determine the minimum frequency electromagnetic radiation, or the maximum wavelength that just barely causes these ionizing transitions. So now it's just a matter of taking this photon energy and setting it equal to, by Planck's equation, hf or hc over lambda, and solving for the frequency and the wavelength. So we'll do these calculations. So for the first photon to ionize the electron from the ground state or first principal energy level to the out of the atom, the infinite energy level, the energy was 2.18 times 10 to the minus 18 joules. In photon energy, the energy of photon is frequency times Planck's constant. So rearranging, we get the frequency. We use the energy of the photon that was absorbed divided by Planck's constant. We get a frequency of EMR of on the order of 10 to the 15th hertz. The wavelength, you can either get that from the frequency and the speed of light, or you can go right back to the Planck equation in wavelength form. The energy of photon equals hc divided by lambda. Rearranging, we get, remember hc is a constant because it's a constant times a constant, 1.989 times 10 to the minus 25 joule meters. The units work out. We get 9.12 times 10 to the minus 8 meter wavelength for that electromagnetic radiation, which is typically recorded or quoted in nanometers because the wavelengths are so small. 91.2 nanometers, which falls in the X-ray region. Remember, 400 is the minimum visible wavelength of light, and then it goes to ultraviolet and then into the X-ray region. For the photon that knocked the electron from the second principal energy level out of the atom, it's a lower energy photon, 5.44 times 10 to the minus 19 joules per photon. Getting that frequency, lower frequency. The lower the frequency of the electromagnetic radiation, the lower the energy per packet, per photon, per quantum of that radiation. And the lower the frequency, the longer the wavelength. So using the wavelength version of Planck's equation, we get 366 nanometers. So that's almost visible, but not quite. Not in the 400 violet region. Ultraviolet light is enough to knock an electron out of a hydrogen atom if that electron is a little bit farther from the nucleus to begin with in the second principal energy level. So that's how you do those. Let's do one more. This one involves an electron losing energy, and people tend to mess up the bookkeeping or the language here. Again, just follow conservation of energy and the appropriate signs and you won't have a problem. So let's see how this works. The electron starts at the n equals 6 level, some excited state, electron energy, and it gets closer to the nucleus, more attracted, loses positional potential energy. So the electron loses energy, goes to a lower energy level. Nothing to memorize there. You're literally saying it's getting lower in energy. Well, that energy can't be destroyed. A packet of energy is formed as a result of the electron losing energy. A photon of energy is formed. And that energy is exactly equal to the magnitude of the energy loss. But energy loss, you're going to see, is of course a negative number. This is a lower number, this is a higher number. So we want to write this out as the negative of the energy lost by the electron is going to equal the energy of the photon, or the energy of the photon formed. We're definitely getting a negative number here because it shows a loss of energy. So there's no way around that. Alright, so the formula then becomes negative. The energy loss is the change in energy. It's another thing that we could write here equivalently, change in electron energy, and that's always going to be final minus initial. So that's energy of the electron when it was in the second level, that's the final state. Energy of the electron in the initial level, and that's going to equal the energy of the photon, which is going to equal HF, which is going to equal HC over lambda, if you want to do those other calculations while you're at it. So looking up the numbers on the chart, we have the electron energies for the second and sixth levels respectively, and we plug them in. Negative 0.38, no, negative 3.40, that's the second level, minus, I'll put the unit after the parentheses, negative 0.38 electron volts. So that's negative, these two negatives become positives, and you have negative 3.02, and of course these become positives. So it's 3.02 electron volts is the energy of the photon that formed, was emitted, got shot out of the atom that had an electron go from the sixth to the second principal energy level. And we could figure that out in joules and the other wavelengths, do those calculations. So as far as the photon energy in joules, you multiply by the conversion factor, and you get on the order of 10 to the minus 19 joules. Anytime you see that for a photon, you know you're near the visible light range. So keep that 10 to the minus 19 joule number ballpark in mind. Using the wavelength Planck equation, Hc over the energy of the photon is the wavelength of the wave nature of that light associated with that photon energy, and it works out to be 412 nanometers, which is visible to humans, violet light. So for that, from that transition, from that single atom, a violet photon would emerge. The frequency associated with that energy photon, the frequency from its wave nature, again Planck's equation, works out to be on the order of 10 to the 14th hertz. Again, keep that in mind, 10 to the 14, 10 to the 15 hertz is right near the visible range. This way you'll have context and you'll know whether you made a mistake. And that's how you do those slightly trickier electron energy loss problems. If you find that you ever get a negative photon energy, number one, that would mean that a photon did not form. The only other context where you can get a negative photon energy, that would mean that a photon disappeared, it got destroyed or absorbed. So had we done this problem using that type of terminology, we would have gotten a negative energy photon, but I certainly didn't want to set it up that way. But for these electron losing energy problems, there's no way the photon formed would have a negative energy. So you'll know you did something wrong. Maybe you didn't write out this initial equation, or you forgot to cancel a sign or something like that. So that's how you do those problems.